We'll start the recording now. And another thing that I almost forgot to try out is that, wow, there are captions now. Very cool. These are actually really accurate. Yeah. Welcome, Tristan. I can address you all by name because there are so few of you. Haha. Anyway. Welcome to Haskell Part 2. I was just getting started. So, yeah, I'm just going to get started then. So let's go to the next slide. So previously, what we covered way back in week 2 is I basically talked about what functional programming is as opposed to procedural programming, how to define variables, how to define functions, how to write conditional statements, what pattern matching is, what arrays are, how to do functions over arrays. So a lot of the basic stuff that you learn when you first get started with any programming language, but with a bunch of extra spicy Haskell things. Don't worry if you're not that familiar with it this workshop, because I'm not going to ask you to code anything. I'm just going to ask you to understand concepts. So yeah, I'm going to keep going. Here's some stuff I missed from last time. I know Ishan had a lot of trouble with indentation when I actually got you to code stuff. So just as a note, whenever you use guards are what you use to write conditionals in Haskell. Make sure to indent. So we have, I can do a laser pointer. Give me a second. No, I can't. Never mind. Wait, can I? Yes, I can. Hey. But anyway, when you use guards, make sure to leave an indent, like a tab, or just make sure it's consistent. Tabs or spaces, whatever your preference is. And make sure to have one blank line in between function definitions as well. That way, when you write Haskell code, you won't get weird compiler errors. Also, these are comments. I didn't mention that, but yeah, that's what those are. Moving on. So here's a quick refresher on what procedural and functional programming languages are. Procedural programming languages are what you've been taught in class for a long time. So like languages like Java, C, C++, JavaScript, they all, well, not necessarily JavaScript actually, but those sorts of languages, basically, when you write programs, what you're actually doing is you're telling the computer how to do something by like saving stuff in memory or moving stuff around in memory. So every program is a set of instructions that you use to tell the computer what to do, and that involves what we call state. So saving stuff into variables, saving stuff into objects, moving that information around. And yeah, whereas functional programming is different in the sense that it's stateless. So functional programming uses only what are called pure functions, which you use to operate purely on their inputs. And you also, it's not really, also in functional programming, you don't worry too much about the low-level details of how something works. The language offers a lot of function definitions that are going to be helpful to you for a lot of different use cases. So you don't have to worry about how to manage memory or whatnot. It's all just there. You just have to know how to use it. So I'm going to move on. Here's a quick example. So just to refresh. So what I have are two functions in two different languages that do exactly the same thing. So these both take an array and a number. Take an array, and what they do is they take all the numbers, I'm assuming that they're all positive, and divide them all by the maximum number in the array. So sometimes you want to do this for like data analysis when you want to take some data and run it on a neural network or whatever, or perform some sort of statistical analysis. Sometimes you want to normalize the data, like convert it between a number between convert everything into a number between 0 and 1. So that's just, that's what these do. So on the left, you have a C program. Don't worry too much if you don't know C, but if you've taken some introductory CS classes, the logic is there. So what this does is that you first have to find the maximum by going over the array item by item, and then you then go through the array again, item by item, dividing each entry by the maximum. So notice here that you have to manually take the array and access each individual index in order to be able to access or change any of the elements. Whereas here we have a function on the right that's in Haskell, and it's, as you can see, it's a lot shorter and a lot cleaner. So what this function does is that it just takes an array and it outputs an array. And here we have a what's called a map. I talked about this briefly. Last time, but what map does is that it takes this function and applies it to every single element inside of array. So this is how you define a lambda function. I'm pretty sure all of you are familiar with what lambda functions are, but yeah. So this defines a function that takes a number x and then it divides x by the maximum in array. So yeah, after running every element inside array with this function, you get a normalized version of that array. So yeah, anyone have any questions so far before I continue to new stuff? Let me open up chat real quick, actually. Okay, I'm gonna assume y'all are good because no one's saying anything, but yeah. So let's talk about extra features that functions have in Haskell, because Haskell's cool like that. So I'm now going to talk about composition. So if you've taken a math class and learned about functions, you've definitely seen this before, actually. So function composition is when you have two functions and you want to take the output of one function and feed it into another function. So you have f and g, and this circle notation is going to be equal to the feeding x into g first, and then feeding the output of that function into f. So Haskell actually has notation that's exactly like this. So if f and g are functions you define in Haskell, this is exactly how you would compose two functions f and g. So let's say f and g both take one argument for just for the sake of example. But oh my god. Yeah, this notation, you have a dot here, which is the same as the circle up here. And f.gx feeds x into g first, and then feeds the output of g into f. So yeah. So here's a quick example of why you want to use that, because it's kind of, I realize this is a lot of abstract detail and not really something you can apply to a program, right? So let's talk about this specific example. So we have some JavaScript code here. And what this JavaScript code does is that you basically want, say you want to take a string and convert it into something that you can add to the end of a URL. If you're like making if you've like worked with Heroku, and you know how a lot of Heroku apps have these, have a string of random words at the end of the URL. This is a way to take some random string and then convert it into something that you can actually put into a URL. So what does this function actually do? So it takes a string, as you can see here, and it splits that string into its individual words by taking everything that's separated with a space and putting it in a separate list called words. And then you loop through that list. You convert everything to a lowercase, and then you take those words and you join them back up with a dash. So again, this is the kind of procedural way of doing it, right? So you go through the words one by one, you convert it to lowercase, then you join them up. So yeah, that's kind of the classical way of programming that we're kind of taught to do things. But let's move on. Here's a functional JavaScript version. So like, I don't know how many of you remember this, but from last time, but JavaScript actually has a lot of functional features, and we can actually use that, and it's actually used really well here. So here we have a function. This function does exactly the same thing as on the previous page. So instead of telling the program, oh, we want to do this, then we want to do instead of like creating extra states to like store intermediate steps, here we just directly manipulate the input. So here we take the string, we call split on it, which splits it up. We call map on it, and then we maps everything to lowercase, and we join it. And notice how all of this is directly manipulating the input, and it's short and clean and nice. So yeah. Here's the Haskell way of doing it. So here's where we actually start using function composition. So yeah, this Haskell function does exactly the same thing. So here we have just a helper function called lowercase. Haskell has a library function called toLower, which converts any character to a lowercase. If we want to apply that to any string, we know that a string is just a list of characters. So we map toLower over every character in the string. Here we have the actual function. So toURL string is equivalent to feeding the input into words, then feeding the output of words into map lowercase. Oh, words, by the way, just takes a string and separates the words based on some delimiting character space by default. But yeah, so takes your string, splits it up into its individual words, maps lowercase on all those words, and then intercalate basically takes a list of strings and then joins them with this delimiting character. So yeah, as you can see, what we have the function composition notation here because we're feeding in the output for this from this function to this function, and we feed the output from that function to this function. Yeah, that's basically it for composition. Does anybody have any questions so far before I move on? Okay, I'm gonna take that as a no. So we're gonna move on. Now let's talk about something called currying. So Ronak put this emoji here, but currying has actually has nothing to do with the food. It's named after this guy, Haskell Curry, who Haskell is also named after, and also gets my award for best name ever. But anyway, let's say we have let's say we have a general function that we want to apply to something more specific, right? So here we have an adder. This is kind of a contrived example, but here we have a function that adds two numbers together. So we have that. And let's say we want to make this more specific. We want to add only 5 to a number, for example. What we can do in Haskell is that you can actually partially apply arguments to a function. So here we have the function add, and we pass only one number into it. What this actually does is that it makes a new function where that takes one argument only. So when you pass in, when you call like add 5, 3, you get 8, for instance. Yeah, that's basically it for currying. What it allows you to do is it allows you to take a function with multiple arguments, add extra parameter arguments to it, and then make a new function from it. This is actually really useful because what you can do is you can make a function. If you want to like modularize your code well, what you can do is make a general function that does things based on a lot of parameters, and then what you can do is that you can just add more specific things as parameters to make more specific functions. One example would be, let's say you had a function that made a general HTTP request, right? There are many different types of HTTP requests. So you have GET requests, POST requests, PUT requests, all that sort of thing. What you can do is you can take your general HTTP request function, pass in specific arguments for different types of HTTP requests, and then make more specific functions based on what you pass in. So yeah. So why are we doing this? One argument functions are nice to work with from a mathematical standpoint. Two, the reason I just mentioned, you can create general functions and then make more specific ones based on those. And I don't know why Ronak added this here, but he did. Very cool. Moving on. Give me a second. Before I move on, anyone have any questions, by the way? Because I know I'm moving pretty fast right now. Does that curry taste good? I hope it does. I don't know. That's up to you guys. All right, I'm gonna move on. All right, now we're gonna talk about something called monoids. So this is where we get into a lot more abstract algebra type things, because a lot of the concepts in functional programming can also be found in abstract algebra, because people love Haskell's an academic language and academics love math. Haha. Anyway, but yeah. So a monoid is basically an abstract name for things that be combined together in some way. How the way they're combined can vary from whatever objects you're talking about, but the basic idea is that you want to have so a monoid is a set of objects that's closed under one particular operation and also satisfies these two rules. So a monoid has an identity element, which means that if you combine a thing with the identity, it stays the same. And it doesn't matter what order you do it. And the operation must also be associative. So math. Yeah. So if you do this first, then do that, then it's the same as doing the second part first and then do you get the idea. Moving on. Here's an example. So here we have strings. So strings are a monoid, for example. So we have strings are monoids. So we take two strings and we concatenate them. That's actually the operation which strings are a monoid under. What this angle bracket funny looking thing here is actually a Haskell thing. So monoid is actually a type that other types can extend from, if that makes sense. So this operator applies to all monoids. So if a type is defined as a monoid, that means it has some operator which you can use to combine the two. This operation is just a generic way of saying, I want to combine these two monoids. So this doesn't just work with strings. It can work with any data type that's also a monoid. So question to the chat. What do you think the identity element of strings under concatenation is? Yeah, y'all got it. So it's the empty string. Because if you combine an empty string with any other string, you just get the same string, right? I have another quiz for you, by the way. So I just gave you the definition for monoids. So based on that, can you tell me which of these operations form monoids over integers? For monoids with integers, yeah. I haven't made a poll for this because it was too much work, but I'll give you like maybe a minute or two to think about it. Okay. I'm just gonna call it there. Some of you got it. Most of you said addition and multiplication, and that's actually correct. Let's talk about exponentiation, because that's actually the important thing I want to talk about. So yeah, the answer is addition and multiplication. Why isn't exponentiation a monoid over integers? Because it's actually
not associative, right?
It's not associative. There you go, Ishan. So if you take like a to the power of b and then to the power of c, that's equivalent to taking a to the power of b times c. But if you do a to the power of bracket b to the power of c, that's not the same thing, right? Is this like closed under? It's kind of like a group. It's not really like a group. A group has a lot of other extra properties that need to be satisfied. But yeah, it's kind of like a group. I think, don't take my word for this, but I think monoids are also sometimes called semigroups, or I don't know if it's a looser or a stricter definition, but yeah, it's weird. I agree. Any other questions before I move on? No? Okay, I guess we're good then. Let's go. So one thing that is particularly mind-blowing about monoids is that it can be applied to any type. So for example, functions. Remember that functions are also types in Haskell. So how are functions monoids? Well, let's try combining. How would we combine two functions, right? So let's say we have these two type signatures where M is a monoid, right? So we have F that goes from A to M and G that goes from A to M. So based on that, this is kind of a hard question, but let's see if you can figure this out. What would the type of signature of H look like if you tried combining these two functions? You can also say that you have no idea. I just would like some feedback. Okay, that's fair. Well, here's a hint for you. Remember that monoids require that the operation be closed under some set. So what set do F and G belong to? Yeah, Zhao's got it. So yeah, so because F and G are functions that go from A to M, G and G's H will also be a function that goes from A to M, because one of the properties of an operator that forms a monoid over a set is that the operation needs to be closed over the set. And what's cool is that H will actually print out will actually return whatever is whatever F returns combined with whatever G returns. And we will definitely be using that later, so remember that. Any other questions, concerns before I move on? Okay, I don't remember what I put on that slide. Did I put it? Oh, okay, cool. So this is kind of where I put a break slide, because the next part is going to be a lot more. I noticed that there was a significant difficulty jump from here on. So is everyone okay? Confused? Just want to get a general sense of how the audience is doing, because I'm just looking at a bunch of blank Zoom square pictures. My webcam is still dead. Oh no. See, this is why professors ask you to turn on your camera, because it's so awkward. I'm just talking to myself. Okay, if no one has anything they want me to go over again, I will move on. Ishan, you're banned. So let's talk about functors. So so a functor is a type of is a type that contains another type. So to be more specific, it defines this function, which basically allows you to, what it does is that it takes everything in every, okay, so a functor is a type that contains another type. So it takes every value inside of that functor and applies a function to it. So think of functors as sort of a way to wrap a value or any number of values actually into some sort of context that you can use for things. I realize this is all very abstract right now, but it will make sense, I swear. So yeah, let's talk about lists, because I'm gonna relate this to what we learned last time. So remember how a functor is a type that contains other types, right? An fmap allows you to apply a function to all values inside of that functor. So my question to you is, how would fmap be defined for lists or arrays in particular? And this would be a lot easier to answer, I think, if you've been to part 1 and it's still fresh in your minds, but it's obviously not. So I'll wait for like 20 seconds. Okay, I'm guessing no one has any idea. That's totally fair. So the answer is actually map. So think of, like I said, think of fmap as a more abstract version of map, right? So what map does is that it takes an array and maps a function over every single value in that array. Fmap is the more abstract version of that. You can take any data structure that's a functor, and then you can apply a function to every value in that type, no matter how the data inside is structured, if that makes sense. I'm actually going to give you an example on the next slide. So this is new notation for, I think, most of you. So I'll go over this bit by bit. So this is how you define a type in Haskell. What A represents here is a generic type. A can be anything. But here we define a data type called tree that contains type A. A tree can either be empty, or it can contain a node that contains 2 subtrees, right? Here we define a tree recursively, but hopefully that makes sense to you. Is anyone confused by this so far? I'm guessing everything's fine if no one says anything, but yeah. And the deriving show is A a keyword or a variable name? A is not a keyword. A is think of it like a variable, but it doesn't contain any value. It's just a generic type. So A can be any type. You can replace it with any type, like int or string or list even. I don't know, but you get the idea. So tree contains type A, and yeah, so tree contains type A, which means that here we have a node that contains the value that is type A. And here we have tree of A and then tree of A. Yeah. Okay. So if we wanted to define, so tree is actually a functor, right? Because it's a type that contains another type, just not in the format that you're used to. So how would you define fmap over this tree? I'm not going to ask you to answer this question because it's hard, but here it is. So this is how you would apply a function to all elements inside of a tree. So what's happening here? So fmap is a function that takes two arguments. It takes a function as its first argument, and it takes the functor as its second argument. So I want to map this function over this data structure. So what happens here? So we define it in two ways. So if this tree on the right here is empty, then we do nothing, right? Because it doesn't matter what we do here because there's nothing to map over. So we just don't do anything. If, however, this tree on the right is a valid node, then what we do is we take this node, make a new node, apply f to v rather, and then we recursively call fmap on the left and right subtrees. So it's kind of like how we traverse trees in, well, it's exactly how we traverse trees in other language, but notice how we don't have to worry about like pre-order, post-order, traversal, or whatever. We just kind of do it recursively, if that makes sense. Anyone have any questions about this? Okay, then we'll move on. Functors can also be extended and made more abstract, for instance. I'm only going to spend one slide on this, but because it's not really, we're not really going to be using this that much, but there are definitely applications for this. So these are what are called applicative functors. So you have, how do you pre-order or post-order traverse it? That's a good question. So let me think about that question. Well, you would. It's just you don't have to think about it in terms of pre-order or post-order traversal. It's like more like my calculation relies on the subchildren of the tree. So I need to be able to get those first before I can continue. I hope that makes sense. Yeah, it is a strange way of thinking, so I understand if it's confusing. Okay, I'm going to continue. So the deal with applicative functors is that functors are values inside of another type. Applicative functors are functions that take values inside of another type. So what we can do is we can actually store functions inside of another type. So what we have here's a contrived example, but here we have two functions, 3+ and 5+. Now, if you remember from currying, what's happening here is that this is actually a curried function. So this takes one argument, and whatever number gets fed into here gets added to 3. So yeah. And we have 5, which takes this, and okay. Yeah, we have the same thing here, but instead of adding 3, you add 5. And what this does is that it applies this function to this data structure, and it applies this function to this data structure. So how this works is that how this is working is that first you apply this 3 to all of this. So you get 4, 5, 6, 7, 8. And then you add 5, apply 5+ to all of these functions here, and you go 6, 7, 8, 9, 10. This operation will come up later, but it won't be immediately obvious as to like how it relates back to this example, but we'll get there when we get there. Just as a warning. because I'm going to go over something really weird. How weird? This is Fizzbuzz. Yeah, it is. If you don't include the import statements, it is 2 lines of code. But if you try running this code in an editor, this works. So let me kind of explain what's going on here. So here we define a function that does something. And then this is helper function. I'll explain what this does later. But what you're essentially doing here is that we're taking, this is an infinite list, by the way. I'll just explain what this is first. So Haskell is what you call lazy, meaning that it doesn't calculate a value until it's needed. What that means is that you can create infinite data structures because it doesn't calculate what this data structure actually is until it's needed. So let's say if I tried to print this, I would go on infinitely because it would just keep printing. But if I were to take an arbitrary number, an arbitrary finite number of elements from this, I could do that because it would just generate it. But anyway, so we apply this function to this infinite array. And what happens is that this converts the number in here to a string that is either 1 or that is either the number, or if it's a divisible by 3 or 5, Fizzbuzz or Fizzbuzz. So this function does all the magic of Fizzbuzz for you. And then we just apply that to every single element of this array. And then we store that end result. So a lot of you are probably really confused about how this works right now, but don't worry, I will go through it. I have done this slide by slide. So some introductory material. So you notice how we have this function from maybe. First, I'm going to introduce the maybe data structure, or the maybe type. So here's the maybe type. So the maybe type is essentially a way to optionally have a value. So here you can see we've defined a data type called maybe, and it takes a type A. It has 2 different forms. Either it is just A or nothing. So either you have a maybe that has a value inside it or it doesn't. And where you could use this, for instance, is say you don't know whether the output of some function is valid. You could instead return a maybe. And if the output of the function is invalid, you return a nothing instead of the just value. And one application where this would be kind of useful is, say you wanted to create a safe division function. You could check whether the second argument is equal to 0. And if it is, you return nothing. Otherwise, you return just first number divided by second number. Any questions about this before I move on? Okay, I guess I'll continue. So here's line 1. So what this function is doing, I'll kind of explain as I go. So let's analyze this from right to left, because that's the order of the functions that are going to be applied to some value. So here we have guard, this function guard. So what this function does is that it returns an object of type maybe. I'm using maybe for the sake of example here, but it actually returns a generic type. But it gets resolved to maybe because we call from maybe on it. But we'll just say for the sake of example that's a maybe. But this function returns a maybe type of object of type maybe that is either just blank or nothing. The 2 parentheses represent a blank value, by the way. So this returns just blank whenever this condition is true, or if this condition is false, then it returns nothing. So we have this, we have some object of type maybe, let's call it. What this operation does is that it takes the value on the left and it tries to put it inside of this whatever the thingy on the left, thingy on the right, right? So what happens here is that we have a string and we have a, and if we have a string and we have a just blank on the right, it becomes a just string. Otherwise, if it's nothing, I forgot to put the syntax highlighting on this nothing, but you have a string, you have nothing, and you get nothing. And what this represents is actually the rule we're using to determine whether we replace the string with just the string or replace it with fizz or buzz. So how does this work? This outputs just string or nothing depending on if x mod m is equal to 0, right? So let's take a look at how this is used here. So here what's happening is that we have 3 squiggly arrow fizz. If we apply this to the number 6, we get just fizz because 6 mod 3 is 0. So let me go back here. 6 mod 3 is 0. So we have guard true over here. That means that this becomes a just blank. Now we put fizz here. So fizz gets put into the just blank. So this returns a just fizz. Over here, what happens is that we have the same thing applied to 4. 4 mod 3 is not 0, it's 1. So we get nothing because there's nothing to stick the fizz into. Likewise, over here, we have 5 and buzz. So if we apply it to 10, we get just buzz because 10 mod 5 is 0. If we apply it to 2, we get nothing because 2 mod 5 is not 0. Here's my question to you. So remember how I told you earlier that functions are also monoids, and that when you combine two functions that both return a monoid, you get another function that returns the combined version of those two monoids. So what should this be? And I'll give you like 30 seconds to think about this. Yeah. Well, yeah, it is Fizzbuzz. So I blame Casey for this because she looked at the slides before, but yeah, it returns Fizzbuzz. Just Fizzbuzz, actually. So, oh, all of you forgot the monoid. Big rip. I used my brain for that. Yeah, totally. But anyway, so what happens here is that you have two functions, one here and one here. When combined, this creates a new function that takes the monoid from that would be outputted from this function and the monoid that would be outputted from this function, and it combines them. So just, maybe is actually also a monoid, because what you can do is you can take two maybes, combine whatever's inside, and then put that in a new maybe. So here we have 15. And when applied to 3 squiggly arrow fizz, we get fizz, just fizz, right? I mean, when applied to 5 squiggly arrow buzz, we get buzz. When we combine the two, we get Fizzbuzz, and we put that string inside of a new maybe. And this is really cool, right? We just took a really abstract sort of representation for the rules of Fizzbuzz, and we just use an operation to combine them. Like, that's cool, in my opinion. I don't know if you think it's cool, but I think it's really cool. But yeah, and we're gonna use this in order to complete our Fizzbuzz function. So any questions before I move on, as always? Okay, looks like we're all good, so I will continue. Now we get to line 2. So this is where things start to get a little bit gnarly. So like I said, we already know what this function does, right? It takes it takes an element from the array that it's given. It should take that number, convert it to a string that is either a string representation of the number itself, or if it's a multiple of 3 or 5, Fizzbuzz or Fizzbuzz. So let's dissect that. So first off, we already know what this part does, so let's condense it into something that's easier to read. So we have a thing called Fizzrules, which does what I described in the 2 slides ago. So now we need to dissect this operator right here. How we do that is actually fairly complicated because it's weird. So here we have a from maybe composed with a function called show. Let me explain what both of these functions do. So from maybe takes a default value and a maybe. If the maybe is in the form just something, it returns the just whatever. But if the maybe is nothing, it returns A. It returns this. What show does is it converts, it basically converts any data type that derives it to a string. In this case, what we're doing is that we're taking an integer and then converting it to a string. So what does this do? Well, from maybe composed with show takes a type A and a maybe string, because show returns a string, and then a string, and then returns a string. So let's dissect that a little bit more. So remember that this is actually a curried function. So from maybe takes 2 arguments. When composed with show, it takes the number that it takes the first argument, feeds it into show, and then feeds that argument into here. So what this does is that it takes the integer and converts it to takes the integer, converts it to a string, and then feeds it into from maybe. The second type is maybe string, because the first argument gets fed into show, and show outputs a string. So now the A over here is of type string. So yeah, if that was confusing, all you basically need to know is that from maybe and show takes 2 arguments, an integer and a maybe string, and it returns a string. So let's move on. Here is the class. Here is the header, function header for this function. It takes an f of A to B. F in this case is another generic type. And remember what I said about functors, right? Functors are types that contain other types. This here is actually an applicative functor because f is a functor and we have a function inside of our functor. And what this does is that it takes another functor of type A and outputs another functor of type B, because it takes the A in here, runs this function on it, and then outputs the result. So let's clarify what that means in this context. So here we have the type signature of from maybe show, from maybe composed with show. And here we have the type signature of Fizzrules. So it takes an integer and outputs maybe string. So this is kind of a hard question, but what is the type signature of this composed with, I shouldn't say that, but the star operator, this? This is going to be a bit difficult to answer, but my hint is that you can also, functions are also monoids. So let me actually draw an annotation here. So think of from maybe composed with show as let me draw some parentheses to help you out. So remember that functions are also monoids. And think of this as returning a function, as a thing that takes an integer and returns a function. Now, if you apply this to here, can you deduce what the output of, I mean, what the type signature of this should be. And if you have no idea, feel free to say so, because I need feedback from y'all, please. Okay. Since no one seems to have an idea, I'm just gonna kind of explain what's going on here. So what actually happens here is that the function signature of this whole thing is actually int to string. Why is this? Let me annotate so I can actually show you. So you have to think of functions as functors here. Functions as not as monoids, but as functions can also be functors in this sense. So here we have our int that goes to maybe string to string. So think of this as a function that takes an integer and returns a function that converts maybe string to string. And the type signature of Fizzrules is what we have here. So we have int to maybe string. So based on the function signature here, let me do another color for this. Give me a second. So this is our type F, and this is our type A, and this is our type B. Here is our type F, and here is our type A. So what would the output of this be? It would be F of B. So it has to be int to string. Does this make sense to everyone? Okay, I'm gonna assume y'all are good because no one's saying anything. But yeah, I realize that this this way of thinking as like having functions be functors is weird and abstract, and it really does take a lot of insight in order to know that. But I don't know. I just think it's cool. Let's clear that and move on. All right. So what actually happens here? So what happens is that we feed an entry from this infinite list into Fizzrules first. So then we call this output Fizzbuzz maybe just for naming purposes so we can refer to it later. Then we also feed that same entry into from maybe .show, from maybe compose with show. Now what happens there, what this does is that so recall that this function actually takes 2 arguments, right? What happens when we apply one argument to it? Well, currying, right? So when we apply only one parameter, we create another function that only takes the last parameter. And then because that last function takes a maybe string, we apply this maybe string that we got from step 1 to this new function. What does this actually look like? Well, it looks like this. So we have here a from maybe composed. We have here from maybe show x Fizzrules x. So what did we actually do here? We took x, fed it into Fizzrules, made this. Then we took x and also put it here. So what actually happens here is that this x will get converted to a string via show. And then from maybe operates on the string version of x and the output from Fizzrules. So for any number, it'll either be string form n or Fizzrules n, depending on whether n is divisible by 3 or 5. This will output just fizz, just buzz, just Fizzbuzz, or nothing. If it's a nothing, this means that x is not divisible by 3 or 5, which means that we only want to keep the default value. So if from maybe gets a nothing as its second argument, it will return that default value. Otherwise, it'll return whatever's in this, whatever's in the second maybe, in this case, Fizzrules. And then, yeah, that basically completes, oh, I'll show you that later, but that basically completes the function. So once we have that, we just map it over everything, and then we get the string. Either we get the number in string form, or we get fizz, buzz, or Fizzbuzz. And this is basically just a way to kind of understand better what's going on here that I just quickly drew out. So here we have a diagram that shows the argument, shows how this function works. So it takes 2 arguments, a maybe string and int, and returns a string. And here is our Fizzbuzz rules. And then those take an integer and output a maybe string, which represents either which is nothing or just fizz, just buzz, or just Fizzbuzz. And then what we do here is that this is what the function looks like after applying the operator to it. So you take this argument, the first argument, you feed it into this function, and then feed the output back into the original function. But yeah, that's basically all I had planned for today. I hope you understood. I hope your minds were sufficiently blown, but I also hope you understood that. If any of you have any other questions, feel free to ask now. But hopefully hopefully you all thought that was cool. But yeah. Oh no. Well, if you got anything out of this workshop, is that CSC 130 is very cool, and you should take it. Yes. I'm going to turn annotations back on, by the way. Oh, I should also stop recording.